Hey everybody, it's Dave Limburg in Hong Kong with another episode of THD Podcast. Today we got another Montreal company. It seems to be a streak going on here. Some guys doing some directional MEMS speakers. So we're going to find all about that. They're called Soundskrit. But first, let's not forget about Alti, the Audio Loudspeaker Technology International, our sponsor. They will be having let's call it a buffet of audio tech at CES coming up in January, where a lot of the members will have little displays of all kind of little embedded audio technologies. So exciting times coming up there. So we encourage everybody to come check us out at CES. So without delay, Simon's in Japan, as always. How are you doing this morning, Simon?
Pretty good, thanks, Dave. Morning.
All right. And then Sahil Gupta and Stephane Leahy joining us, the founders of Soundskrit in Montreal.
Hey, Dave. Thanks for having us.
All right. Very cool. So, let's just maybe introduce yourselves, and then we'll jump into a presentation on Soundskrit.
Sure. Yeah. So I'm Sahil Gupta. I'm one of the co-founders and VP of product over at Soundskrit. Backgrounds in electrical and computer engineering. Did my graduate degree focusing sort of on MEMS sensors. Also love everything audio, been playing music my whole life. So Soundskrit was sort of a natural fit for me to kind of bring those two parts of my life together.
All right, cool. Stephane?
Stephane Leahy. I'm one of the co-founders and the hardware VP at Soundskrit. My background, I have a PhD in MEMS, and I also I play some guitar. I've recently realized that I have a bit of I can't sleep when I hear the sound of a clock ticking. So I feel like, I don't know if it's just through working in audio for so long, but like maybe it's affected me a little. But I'm really passionate about figuring out kind of new tech and troubleshooting.
All right, cool. So yeah, let's maybe jump into a presentation and walk people visually through an introduction to your company.
So just a little bit about Soundskrit. We are an audio company, really trying to rethink how we capture sound. For us, that's really enabled by this new type of directional MEMS microphone, which we'll tell you a bit more about in a second here. As you mentioned, we're headquartered in Montreal. We have an R&D facility over in Ann Arbor, Michigan. We're a team of engineers, musicians, tech enthusiasts that kind of came together around this project. We originally spun out of an incubator called Tandem Launch. It's based out of Montreal. As part of this incubator, we kind of look at kind of deep tech coming out of universities, sort of university innovations that might be sort of compelling specifically for the consumer electronics space. And so this particular technology spun from some research of a professor. His name's Ron Miles, who's a professor over at Binghamton University. Spent the last 35 years looking into different types of MEMS microphones and things like that. And so we'll talk about that in a little bit here too. We officially announced the release of our new product, the SKR 0400. It's a MEMS directional microphone. We announced it about 3 weeks ago. Honestly, it was just really exciting for us. We've been working really hard, the team back here, for the last few years to kind of get this thing together. And so to finally be able to kind of show everybody what we got and talk about it, it's super exciting for us. We've been sort of overwhelmed the last few weeks with folks reaching out. And so it's just super cool to see the kind of outreach that we've been getting ever since we announced this thing.
All right.
I did say that we're an audio company. And so while our core technology is sort of this new piece of hardware, we also develop software as well that kind of takes the output of our hardware and tries to clean up the audio to do a variety of different things. We have everything from kind of your traditional audio signal processing to lately we've been getting into some more AI-based processing as well. We do everything from taking an audio signal and trying to clean out the background noise and reverb to really isolate a user's voice and clean up the audio. We do things like tracking one or multiple speakers around a room. We've kind of had demos where we can get not only just the direction of somebody, but also the distance they are from the microphone. In terms of distance, it's not like a measuring tape here, but at least getting some sense of if they're close, kind of a few meters away or really far away. One of my favorite features that I guess we'll talk a little bit more about is around what we're calling true stereo capture. If you're familiar with professional audio recordings, the way that they get really awesome stereo capture and sort of immersive spatial audio recordings is through the use of directional microphones. So the ability to kind of miniaturize that into consumer form factor is very exciting for us. And then, for us, while we're working on this microphone, we're all about the user experience here, right? And I think the fact that we do software allows us to really think of everything, not just from the hardware and the component level, but all the way up to the kind of the feature. Before we go into some of the features and applications though, I'll pass it over to Stephane, who will give some context into why we even need directional microphones in the first place.
So omnidirectional microphones, they're widespread, right? They're readily available, they're all over. But unless you're in a studio, you'll rarely see, a system or a product with just one of them, right? You'll have an array of microphones. And why? It's because the omnidirectional microphone itself captures sound from all directions. And in almost every application, what you want to do is you want to maximize the signal quality of the user, and then you want to reject the noise coming from the other direction. So you use an array, right? If I think of AirPods, or if I think of many popular products, phones, there's multiple microphones, and they do that to get directionality. So the fundamental beamformer is actually a differential beamformer, and what you do is you subtract the output of two omnidirectional microphones, and then this gives you a directional system. And one of the ways to quantify the directionality of a system or a beamformer is to use the average directivity index, which is it's the logarithmically weighted average of the directivity index over the audio spectrum. So on the right, we have a graph that's we're showing the directivity index for different differential beamformers that have different amounts of spacing. And so this directional index is actually as a function of frequency, because it's basically a measure of how much sound power on axis versus the sound power over all the other directions. And we measure that at each frequency, and then you can integrate that and you can get a final number. And so what we see is that for a differential beamformer, the smaller the spacing, the higher the DI. And for 10 millimeters, you got 4.6. The ideal is 4.8. And you can see that blue line, it's almost flat across, and it just starts to tape off at higher frequency where there's aliasing. Exactly. And then as you increase the spacing to 40 millimeters, you start to get aliasing earlier, and then 75 millimeters even earlier. And you can see that the DI really drops significantly. So to get good directionality in a system, you need small spacing.
Interesting.
So not that hard to put the two microphones closer together. If anything, people like small systems and small spacing. So where does the trouble come? Well, the trouble comes from the fact that when you take the difference between two closely spaced microphones, you lose sensitivity. So here we took a measurement of two state-of-the-art omnidirectional microphones, 70 dB SNR, so one of the highest signal to noise ratios available on the market. And on the right, we're showing a measurement of sensitivity. So normally you'd see a flat sensitivity for just a single mic, but when you take the differential system, the sensitivity depends on the pressure difference, and that is changing as a function of frequency or wavelength. And you can see that it actually drops, from -20 down to -80 at low frequencies. So you really lose a lot of sensitivity at low frequency, and your noise remains the same. So that leads to really low SNR. For this state-of-the-art system, we call it the directional SNR, is only 53 dB, which is unacceptable for a lot of applications, because now you have all this noise in the system.
Okay.
So what if we instead build the directionality into the hardware itself? So we get the directionality and the SNR, can we do that? It turns out that most animals use directional auditory systems, and they don't only use these to communicate, but they use them to survive. So Sahil mentioned our inventor, Ron Miles from Binghamton University, and he's studied microphones and the auditory systems of insects for his whole career. And what he realized is that insects and other animals have actually very good directional auditory systems. And he noticed that for a lot of them, actually, what they do is they even though they're small, they can get very good directionality and signal, and they actually sense the airflow instead of the sound pressure. And they use like the hairs on their body, so they can orient them in different directions, and they basically they have a very good ability to locate sounds from different directions, which is an advantage for survival. So what we did is we teamed up with Ron Miles. He actually together we built our first prototype with gold coated spider silk. So it was about this big, and we had to harvest silk from spiders, and we hand built it, and that was our first prototype. And so, well, what we've done since is we've really uncovered the physics and then translated this to silicon.
Okay. Must be some kind of interesting material science to get. Would you call it little microcilia, or what would you call these? Like,
well, I mean, when we started out, we were wondering, should we go try to like commercialize this with spider silk? Because there's actually some companies that are, that, but we quickly realized that wasn't going to be the way to go.
Right.
So on the right, there's an SEM of one of our early prototypes, and it's so that's made out of polysilicon, typical MEMS materials, and we just had to figure out the physics. How are the insects doing it? What was it about their system that gives them the performance?
Okay.
Yeah, part of it's how we just kind of mechanically build this thing to move well with the surrounding air, right? More than using some kind of exotic material or something like that.
Okay.
So as Sahil mentioned, we recently launched our SKR 0400, the first high-performance MEMS directional microphone on the market. And so I'd like to look at the cross-section on the right here. So you can see that our package has all the similar components as an Omni, right? There's a PCB, there's a lid, there's an ASIC with glob top, and then there's a MEMS. One difference you'll notice is that we have a second sound port in the lid. And what that sound port does is when sound comes from the bottom or the top, it passes through the MEMS. But if it comes from the left or the right, it comes across and strikes both sides of the MEMS at the same time and basically cancels out the pressure difference. So that's what makes it inherently directional. And then, putting the hole in the lid was easy enough. But then we completely redesigned the MEMS transducer so that we get higher sensitivity to get the performance. Because as I mentioned, right, it's easy to get just SNR, just an Omni, or just directionality, two closely spaced Omnis, but getting both of those things, SNR and directionality, is really the hard part.
Just kind of an off-topic question, but glob top, is that just another word for the packaging of the ASIC?
The glob top is actually, it's like a black material that covers the ASIC to protect it from light and corrosion.
Yeah.
And it just goes over the circuit.
Like a package for a chip type.
Yeah.
Okay. Yeah.
Well, it's actually like a kind of a liquid that they pour on it, and then it solidifies. Almost like a black glue, epoxy kind of.
Okay. Yeah, it's self-describing, but I haven't seen that word before. Thank you.
Yeah, we've used it a lot, but I didn't know about it until getting into MEMS.
Okay, cool.
Yeah, glob. All right, so now let's look at our directionality. So again, we're looking at the directivity index as a function of frequency. You can see on the right, the graph, we have a flat 4.8 dB at all frequencies, and when we take the average of that, we also get 4.8. So we got excellent directionality. On the bottom, you have the polar plot, so you can see that we have the ideal polar pattern at all frequencies, both at low frequencies and at high frequencies. So we don't have that aliasing problem that the microphone arrays were experiencing.
Yeah, and just to add on to that, I think this is something that people have been really excited about, right? It's very difficult to get something that's super consistent all the way down to 20 hertz, all the way up to 20 kilohertz. So this is something that we're really excited about, and I think becomes a really cool tool when we start thinking about how we can use this and start adding software on top of it as well.
This directivity index of 4.8, is that something that corresponds to a 4.8 dB of attenuation to off-axis sounds, or it doesn't correspond like that?
So if you had diffuse sound, so if I had kind of noise coming equally from every direction, I would reduce that noise by 4.8. But if I look at something like the null at 90 degrees, I'm getting over 20 dBs of rejection at that specific point. So, it depends a little bit on your environment, right? If I diffuse noise, I get 4.8 dB. But maybe if I had like somebody talking or a direct sound source like a TV, you could do more clever things like steer the null towards that direct sound to get even more attenuation.
Okay. So yes, it is an attenuation dB figure, but it's averaged over all angles essentially.
Exactly. Yep.
And we didn't invent that metric. We just dug it up, right? It's a common metric used in pro directional microphones, and then if you look at a lot of research papers use it, but it's not with omnidirectional microphones. I guess it's not as commonly seen. So we kind of resurfaced it, and we're pushing it now because we've realized that that's the way we can quantify it. Yeah. All right. So we showed we got the directionality. What about the SNR? So what we did here, we're comparing a measurement of the sensitivity and the noise of the SKR 0400 versus the 2-mic omnidirectional array in a 10 millimeter spacing. So I showed the 53 dB number before for the omnis, and then you can see that Soundskrit we're providing 63.5. So a 10 to 11 dB improvement in SNR over the state of the art, which is a big jump. And therefore, right, we can replace the traditional microphones array with a smaller footprint, lower power consumption, and less computational complexity. And then we often get this question is like, okay, well, you have a directional microphone pointed one direction, but what if you have someone that's coming from another direction? Is that just going to be, are you just going to reject their sound, or like, what are you going to do about that? So what we can do is take two Soundskrit microphones and place them orthogonally. And that way we can capture sound from along two axes, kind of like on a coordinate grid. And we can actually steer the beam using vector math, right? If we take half of the y and half of the x, we get in between, and we can basically steer it and do a lot of cool demos. One thing we never agree on is which way is actually the x direction. Is it the way that's facing the user, or is it the opposite direction? So that's one where there's no convention. But regardless, right? If you have two of them that are orthogonal, you can steer it. And yeah, I think we can do all sorts of. I mean, we got a ton of demos online that show what we can do with this, and it's a pretty popular solution among some of our early customers.
Yeah, so I think the next question that kind of comes up is how can I use this, and maybe what are some of the applications of this? So I think one of them that kind of is an obvious winner is around background noise rejection, right? I think especially over the last few years with people working remotely, we've all kind of had that remote call where you hear someone's kids coming in, or their dog barking, or the TV in the other room. That's a problem of directionality, right? The better I'm able to kind of pick up sound from one direction and block out the other sound, or the sounds coming from other directions, the more I can really isolate a user's voice and maintain really kind of high fidelity call quality and things of that sort. Things that we can also do is with our software, we can kind of enhance the directionality by recombining those two microphone signals or kind of broaden it up. So, when you start thinking about pairing this with things like a webcam, for example, you could imagine having the directional microphone zoom in with the camera, or zoom out with the camera to give you kind of a narrower or wider field of view. Another area around reverb. This is one that I personally frustrates me. So I live alone. I'm in my apartment right now. It's totally quiet. I'm just in my room, and I still have to wear a headset to go on this podcast, right? The moment I take off this headset, or God forbid, I step a little bit farther away from the laptop, my sound is going to get a lot more echoey. It's going to get a little bit muddy. It's going to be a little bit less clear, right?
Yeah.
And that's reverb, because I have all these walls and these tables and surfaces around me. And so when I talk, the microphone's not just picking up the voice from where I'm talking, but it's also picking up all the reflections off these objects around me. And so really the best way to get rid of reverb is directionality, right? If I can kind of block out all those reflections from other directions, I can just maintain that main sound source and get kind of more of a dry headset like podcast like audio quality. One thing I thought was worth mentioning was also, more collaborative environments, right? So think about a bunch of people around a conference table, whether it's a conference speaker, a webcam, or even you place your laptop in the middle of a table. We don't just, like Stephane mentioned, when we use this XY configuration, we're not just picking up sound from a specific direction, but we can dynamically change where we're listening, right? So now you imagine somebody who's not like tethered with a wire to their laptop like I am right now, but they're actually moving around. Well, because we can understand where they're coming from, we can actually steer a beam and track them. Or even if there's multiple people, we have some really cool demos where we have multiple people talk to our microphones at the same time, and we can actually simultaneously transcribe them in real time and separate out their speech, right? So, I think this can be really interesting for more collaborative type environments as well. One of my personal favorites is probably just the former music player in me, is around kind of this stereo or spatial audio recording piece. I'm not sure how familiar you are with like professional audio recording techniques, but when they want to get stereo in kind of a professional setting, they take two directional microphones and they point them in different directions, right? They'll send one channel to the left, one channel to the right. And then when you play it back on something like a headset, or even laptops now, or phones, they're starting to do some more spatial audio playback. You can kind of hear that sound pan from the left to the right.
Yeah. People might see those little digital recording devices, and they always have two little mics.
Yeah.
And so guys going out and, sampling the stream or the birds and stuff like that.
Yeah, exactly. Actually, we used to use one of those back in the day just to kind of compare it to, but those things are big, right? And so they're obviously like plug-in accessories, but now we've miniaturized it to the MEMS scale, right? These things, you could have two microphones like that, but it's smaller than a coin, right? So you can imagine putting that into a camera, a mobile accessory, or things of that sort. And what I find at least is a couple things. I mean, when you listen back to that audio recording, you kind of feel like you're there, right? Like you're in that actual room. And another thing I found kind of interesting is we spend so much time trying to like reject noise and reverb. But when you play it back to somebody in a stereo setting, you don't mind noise and reverb and things as much, right? Like your brain kind of naturally takes those cues and just kind of puts yourself in that environment. So, this is something that we're talking to a lot of customers and folks about as well. One area that I'm excited about is around kind of TWS or like kind of the wireless earbuds that we see, I think, proliferating in the market today. Microphone arrays fundamentally need space to work. One of the reasons, like Stephane showed, if you bring them too close, you lose a ton of SNR. So you got to keep them far apart. These earbuds are getting smaller and smaller every day, right? And so you don't really have the space to put them, 4 centimeters, 8 centimeters apart, like you might see in a smart speaker, a laptop, or something like that. And so I think in those really small space constrained devices, that's where our technology can be really compelling. Again, our microphone is no bigger than a single omnidirectional microphone. So you can imagine sticking this thing in like an earbud, pointing it right at your mouth. And now, you don't need to use DSP or computation to get that directionality. You get it in the hardware itself. Something that we've been playing a lot with as of late is also changing the directionality pattern of our microphones. So we can do this in two ways. You can kind of combine it, a dipole microphone with an omnidirectional microphone, and you can create different types of cardioid and hypercardioid type beam patterns. And you can also mess with the packaging around the microphone to do this in hardware as well, right? So we're able to get a variety of different directionality patterns based on the application and the needs. And then maybe a final thing that I'll talk about is, we've talked a lot about like voice and audio capture itself, but I think there's also applications where it's not so much about sending through audio, but it's more about how can we listen to audio and use audio to just become a little bit more aware of our environment, right? I think the security camera is a good example of that. We often hear things before we see them, right? So you imagine something like this on a security camera, and the moment you hear a loud sound, you can understand where that sound is coming from, and maybe you steer the camera in that sort of direction, right? So I think, audio becomes a powerful tool for more than just kind of voice or audio pickup as well.
Right.
So, that's kind of what we had for you here today. We obviously have a lot of information around this stuff, so happy to chat about whatever you guys want to. But, I think in general, we're super excited about this stuff, right? We've been working at this for the last few years. And if you get a chance, I encourage you to take a listen to some of our demos on our website. I mean, I think they really speak for themselves. The performance we've been able to get out of these things is quite incredible. So we're pretty excited here.
And it's soundskrit.ca, is that correct?
Yes.
Okay, we'll put that up on the screen for you here. So like in terms of like roadmap, I know everybody's trying to get more SNR out of MEMS. So I can just try to predict things, but would it be like trying to maintain SNR and bringing the proximity of the mics closer together? Like what would your roadmap kind of look like for what you're targeting?
You want high SNR in the small spacing, right? So you're always trying to improve SNR. We are, and so are the competitors. But because they designed their microphone to be omnidirectional, they're basically starting out at 53. So they've got, right, and then there's actually limits in terms of thermal noise of the mics as well, because you have different noise contributors. You have the ASIC. You have the thermal noise of the membrane itself with the air particles. So it gets harder and harder to get to those limits. But yeah, I would say that our roadmap is to come out with the even higher SNR. We've got some designs cooking.
When you're talking about SNR in this context, it's as a consequence of low frequency attenuation. So it's,
or we could call it directional SNR, where it's like, okay, I want a microphone system with directionality. To get good directionality, I need small spacing. Let's calculate the system SNR, after you've gotten the directionality. So it's like basically the SNR after you've taken the difference of the omnis and not just the omni itself.
Sure.
Because that's what matters ultimately.
Yeah, but that final signal, then SNR of that final signal, but the actual noise floor of the microphone isn't changing. It's that you've attenuated the
sensitivity
primary signal and mostly in low frequency.
Yeah, exactly. Yeah. So exactly.
As you approach 0 hertz, you go to infinite attenuation.
Exactly. Because of the way a sound wave travels, or the pressure difference depends on frequency. And you're basically trying to get more signal with a smaller pressure difference. So how do you do that? You can improve your transduction efficiency. So for less force, how do I get more voltage out? Because the noise floor is going to stay the same.
Okay, so for a Soundskrit microphone, you still have that dropping low frequency response characteristic.
Yeah.
But if you preserve enough SNR, you can just equalize that back to flat.
Yeah. So equalization, we've actually went over equalization quite a bit with different customers, and so any system will be equalized, and basically the SNR doesn't change whether you calculate the SNR unequalized or equalized. we have an app note that explains how to calculate the SNR. If the response is flat, you can just use the sensitivity at one frequency at 1 kilohertz because it's the same everywhere. But if it's not flat, then you got to use it at each frequency. And if you equalize it, it comes to the same thing because you basically equalize your noise as well.
I see. Okay.
Yeah.
And in terms of how you actually implement these MEMS into a product, you have to expose both sides in a pretty even fashion to external noise.
Ideally we'd have the both path lengths the same. We can, it depends. So when you're a tube, the acoustics in a tube depend on the length of the tube and the size of it. So you gotta figure all that out. But essentially the simple answer is you'd want the paths to be symmetric. You can also do some cool things when they're not symmetric, or like when Sahil said, if you add certain meshes, you can change the polar pattern. So there's, I would say it depends on the design you're looking for.
You can also really play like with where you place sound ports and things like that too. So this is something that we spend a lot of time looking at is, obviously that the microphone itself has a sound port in the front and the back, but imagine making like a U or something where the microphone kind of sits in the middle of the U. Now you can put both ports on the same surface and the sound will kind of come in, hit the microphone and come out. And so there's a lot of ways that we can kind of mess with the packaging to kind of point the beam in a certain direction or just place ports in certain areas. And I guess the important thing, like Stephane said, is just to be cognizant of how long those acoustic channels are, how wide or narrow they are, and just kind of be cognizant of those design constraints.
Yep. Do you think that, say, in a TWS earbuds design, you could end up with decent performance just by putting the microphone, the one port to the outside, the other port just into the internal volume that's sufficiently leaky that for most of your bandwidth, you get a reasonable approximation?
It'd be better to have both ports exposed, right? It depends, pointing one of the ports into an internal cavity of the ear is gonna have some pretty traumatic effects on the directionality. We'd have to run some numbers, but what we're looking at is having them both pointed out.
Okay.
On the outside of it, right?
Yeah.
Or like a headset right here, just having kind of two holes that point this way.
Yeah. So then in the design, you're always going to be building around having these two paths, equal paths to front and back.
Yeah, or similar, right? Like, so if you have two omnis, you have basically two tubes, each going to an omni. So now we have those two tubes and then the MEMS in the middle. So they're kind of connected horizontally. And then, you decide on what you want to, what do you want to choose for your design? Do you want the ports to be really close with lower SNR but better directionality? Do you want them to be further? There's trade-offs, but the way we benchmarked it, like basically in those slides, we said, okay, let's do 10 millimeters and 10 millimeters, and let's see, let's look at SNR and directionality.
Okay, and then in a like a gaming headset boom mic application, it's pretty simple, is it?
That's easier. Yeah, you could just have the through hole, right? You could just have it there. Yeah, so that one's definitely easier.
And how, in that application, how does it compare to an Electret directional microphone? A standard capsule.
Right. So Electrets, actually, I remember going through DigiKey a while ago. I think most Electrets are below 70. They're probably in the, I think mid 60s, low 60s. So some of them have pretty good SNR. They have all the drawbacks of Electrets, which is like they're super big, right? So they're maybe 6 millimeters in diameter or 8 millimeters in diameter. So they're way bigger than the MEMS. And then, the stability with temperature and over time. So a big Electret can do pretty well. And I mean, that's what a lot of pro microphones are, either the condensers or the Electrets, right? And they're really big. Like the microphone you're using now, David, I think I don't know if it's in cardioid mode, but it's probably at least a 1-inch capsule. So 25 millimeters, right? Our microphone diameter is about 1 millimeter. So,
okay, so that application, then it's fair to say that the advantages of using a MEMS, you can SMT it onto a flex, etc.
Exactly. Yeah, the size, all the same. Yeah.
Okay.
One thing we're also talking to some folks about with like the boom is what happens if you kind of put like an XY and try to do something a little bit more sophisticated. So not just obviously the simplest case is just to point a directional beam to your mouth. If you think about one of the reasons MEMS, I think, took over electrets, at least in the omnidirectional space, is like sensitivity matching too, right? MEMS can be really well sensitivity matched, so you can get a little bit more sophisticated with the software. So now what happens when I have an XY in my boom? Can I not only just pick up my voice, but also kind of pick up some of the ambient noise and use that kind of reference to kind of cancel this out? If you think about like a dipole or something with a null towards my mouth, now I'm not picking up my voice, I'm just picking up the noise, right? So I can kind of use that as some more information to further clean up my audio.
Right.
Yeah, it also helps the roadies with people that aren't using their mics properly. They're going off and they can get a better pickup.
Right. That's
so many
true.
times.
Absolutely.
Yeah.
Or you're doing like, you're moving this thing around and
It's actually, it's such a simple problem, but like I was at a wedding last week and the person was talking and moving and it disrupts the speech so much, and I guess they don't notice it, but
You don't realize it because it's still in their head. It sounds
right.
great.
Yeah, exactly.
But
so it's the challenge of the audio, right?
Yeah.
Go ahead, Simon.
Oh, and then you're talking about tracking users' voice and finding distance and things like that. That comes into play when you put in a pair or triple of these microphones and start doing some computation on the relative signals.
Yeah, a lot of that stuff comes with this kind of XY or a pair of microphones, right? So we get kind of two signals that we can compare to kind of understand things. With a single microphone, the directionality will be fixed, right? So maybe if I put it on a camera or something where, it's always pointing at the thing that I want to listen to, it makes sense. One thing I think I forgot to mention that I think is interesting is right now everybody relies on software to kind of clean up audio. And so the software is only as good as the input into it, right? So if I take the same exact, single channel AI or single channel noise reduction, I give it the signal from an Omni, it's picking up all this ambient noise. The software has to work really hard to clean it up. And so while it's cutting out all these chunks of noise, it's also cutting out chunks of your speech. So it leaves your speech kind of distorted, a little bit robotic, unnatural. If I just take a single directional microphone, give it to the same software, I've reduced that noise. The software doesn't have to work as hard. So it gets rid of that last bit of noise, but then your speech is preserved much better, right? So I do think a single Soundskrit microphone has advantages when we look at kind of like single channel noise reduction and software. But for sure, for some of those more advanced features like tracking and steering around a room and things like that, you'd want a pair of these.
All right.
Yep. And some of the cases are talking about noises in the background. Is there some relationship between the directionality and its effectiveness against near field and far field sources?
The more directional it is, like the more proximity effect you'll kind of get, if that's what you're talking about, right? So if I make something that's super directional, it's gonna boost up that near field versus the far field for sure.
And this because of far field sounds will become kind of uniform?
Yeah, exactly, because it's like a plane wave in the far field versus when it's like spherical in the near field. You get a little bit of a bass boost, right? Kind of the same reason whenever you take like a podcast microphone or a singer, like when they sing very close to the microphone, their bass is a little bit louder, right?
Yeah.
And so for manufacturing, these could be made almost anywhere. Have you guys got a base set up for manufacturing already?
Yeah, absolutely. So we do this overseas. And in our R&D facility in Michigan, we have our own fab engineers. We develop the whole fab process. We have an R&D facility where we can kind of prototype stuff. But then, for mass production, we're set up with a foundry overseas. This is a very straightforward process. What we tell folks is, kind of any foundry that can run a traditional MEMS process can run this thing. We're not doing anything super crazy or exotic.
And commercially, are there existing distributors like in Asia or in US or wherever that's stocking your parts, or that's coming soon, or where are we at?
Not at the moment. That's something that we're actively starting to build out now. We just released this product a couple weeks ago, so that's kind of the stage we're at now, is building all that out.
I'm sure the funders want to know when that plan comes in.
Yeah. But we are working with a variety of customers across several different applications, and webcams, laptops, AR, VR. We're working with a few headset guys, so we're actively working on getting designed into some parts, and so hopefully this next year we'll have some more good news that we can share.
Okay, cool. Any more questions from your side, Simon?
I think they'll cover it.
All right. Okay. Well, thanks, Sahil and Stephane, for joining us today. We really appreciate that. Some interesting stuff, and very timely, like all these webcams and all this kind of conferencing type devices. It's kind of key to detect and pick up and focus on who's talking. So that's very cool. So yeah, if there's nothing else, let's table this for today. Encourage everybody to like, subscribe, share, all that good stuff. And we'll see you on the next one. Thanks, everybody.
Yeah, thanks so
Sounds
much for
good.
having us.
Yeah, thanks, David,
Bye-bye.
Simon. Take care.